Scientists have long believed the universe is very, very old. Nearly 13.8 billion years old is the common estimate. But now, this belief, based on years of observations and calculations, has been flung into question by a new study based on the James Webb Space Telescope's latest observations. The new shocking study revealed that our universe could be twice as old as current estimates believe it is. That challenges the dominant cosmological model and sheds new light on the so-called impossible early galaxy problem. But does it hold true? And was the Big Bang Theory wrong? All this and more in today's episode of Eyes 200M. The James Webb Space Telescope, or JWST, was built to revolutionize our understanding of the universe. Stationed 1.5 million kilometers away from earthly interference and chilled close to absolute zero by its tennis court-sized sunshade, the telescope's giant segmented mirror and exquisitely sensitive instruments were designed to uncover details of cosmic dawn never before observed. This is the scarcely probed era, no more than a few 100 million years after the Big Bang itself, in which the very first stars and galaxies coalesced. How exactly this process unfolded depends on exotic physics, ranging from the uncertain influences of dark matter and dark energy to poorly understood feedbacks between starlight, gas, and dust. By glimpsing galaxies from cosmic dawn with James Webb, cosmologists can test their knowledge of all these underlying phenomena, either confirming the validity of their best consensus models or revealing gaps in understanding that could herald profound new discoveries. Such observations were supposed to take time. Initial projections estimated the first galaxies would be so small and faint that the Webb telescope would find at best a few intriguing remote candidates in its pilot investigations. Things didn't go as planned, though. Since it first started sending back science data in mid-2022, the internationally funded, state-of-the-art JWST has been giving us images of distant galaxies that appeared to have formed and matured far earlier than our models predicted. Webb's haul of galactic baby pictures has proved more bountiful than most researchers dared to dream. Simply put, candidate galaxies in the early universe are popping up in numbers that simply defy predictions, with dozens found so far. It's enough of a problem that some are calling it a challenge to our entire cosmic timeline. According to the standard model of cosmology, after the fiery Big Bang 13.8 billion years ago, the universe cooled and energy turned into matter and eventually coalesced during the first few 100 million years, forming the first generation of stars and galaxies. Astronomers thought they had a decent understanding of this process. But James Webb's initial results may suggest that stars and galaxies were forming far faster than anyone expected. The telescope had done nothing less, read the headlines, than break the universe and upend models of cosmic history. Subsequent data have ruled out some of the more dramatic findings, and new simulations can accommodate at least a few of the strange observations. But some bright, massive, and early galaxies continue to confound theorists, suggesting that our understanding could shift in the coming years. According to Priyamvada Natarajan, a theoretical astrophysicist at Yale University in New Haven, Connecticut, no data at the moment has broken the universe, but I think there are interesting potential tensions emerging on different scales, Natarajan said. Resolving these tensions will require researchers to revisit their fundamental assumptions about galactic evolution, and that could mean bringing new ideas to the forefront, while leaving others in the cosmic dustbin. Prior to the launch of James Webb, no one knew if galaxies could ever form so early in the universe's 13.8 billion year history, at a time when matter was thought to still be sedately coalescing into the gravitationally bound clumps required to give birth to large groups of stars. As Garth Illingworth, an astronomer at the University of California, Santa Cruz, said in a press conference held by NASA to announce the peer-reviewed validation of the first two candidates. And so we're wondering, do we really understand the early phases of the formation of these galaxies? This has posed a lot of questions for the theorists. Chief among them is how exactly dark matter guided the emergence of galaxies. For the first few 100,000 years after the Big Bang, the cosmos was so hot that gravity could not pull normal matter together to form large protogalactic clumps. Yet this was not an issue for dark matter, says Georges Penarubia, a cosmologist at the University of Edinburgh in Scotland, because dark matter does not interact via electromagnetic forces, he said. Instead, gravity alone is this invisible substance's master, meaning that in mere moments after the Big Bang, when primordial chaos otherwise reigned, gravity immediately began glomming together dark matter into large clumps known as halos. These dark matter halos are believed to have acted as gravitational sinks for normal matter, seeding the subsequent formation of galaxies in the early universe. The telltale motion of the stars they shepherd betray their endurance to this day. Such halos still surround galaxies like our own, majestic but invisible sculptors of the modern cosmos. James Webb's rapid discovery of early galaxies might be testing our understanding of how these halos form, perhaps suggesting they reached an immense bulk earlier than expected. One explanation might involve the very nature of dark matter itself. Theorists have found that simple treatments of dark matter, in which it only interacts with itself and normal matter via gravity, can accurately replicate large-scale cosmic structure. But nature has no guarantee of simplicity. In reality, dark matter could interact with itself because of an as yet unknown force, perhaps via a particle that's not in the current standard model of physics, possibly increasing the speed at which these halos grew and explaining how big, bright galaxies were able to arise so quickly. However, perhaps instead these halos were simply more efficient at drawing in regular matter to feed star formation. I think this is probably telling us something about how stars form in dark matter halos so early on, Penarubia says. Today our galaxy produces roughly one new star per year, but Castellano's paper suggests that star formation rates must have been at least 20 times higher in his and Naidu's two candidate galaxies. Another JWST-derived preprint paper posits that Milky Way galaxies could have arisen just 500 million years after the Big Bang, a scenario that would demand star formation rates 10 times higher still than Castellano's estimates. But according to Michael Boylan-Colchin, a cosmologist at the University of Texas at Austin, such outsized rates of star formation stretch the boundaries of what is physically possible. He says, if those values are correct, you'd need to have galaxies turning all their mass into stars and forming stars as fast as they could. Researchers have likened the impossible early galaxy problem to flipping through someone's old photo album, expecting to find baby pictures, and seeing a full-grown adult instead. With a person, you might just conclude that they're older than you thought, but with early galaxies, you very quickly run into a problem with the age of the universe itself. For generations, people argued about whether the universe had always existed, whether it had a beginning or whether it was cyclical, with neither a beginning nor an end. But starting in the 20th and continuing into the 21st century, we not only drew a scientific conclusion to that question, the universe as we recognize it began with a hot Big Bang, but we were able to pinpoint precisely when the beginning occurred. The simplest and most straightforward way to measure the age of the universe is simply to look at the objects that are in it, stars, for instance. We have hundreds of billions of stars in the Milky Way galaxy alone, and the overwhelming majority of the ancient history of astronomy was devoted to studying and characterizing these stars. It remains an active field of research today, as astronomers have uncovered the relationship between observed properties of stellar populations and how old they are. The basic picture is this: a cloud of cold gas collapses under its own gravity. leading to the formation of large numbers of new stars all at once, that come in all different masses, colors, and brightnesses, and the largest, bluest, brightest stars burn through their fuel first. Therefore, when we look at a population of stars, we can tell how old it is by looking at what types of stars still remain, and what classes of stars are completely gone. Our galaxy has stars of all different ages in it, but the measurements of any individual star will be riddled with uncertainties. The reason is simple. When we view an individual star, we see it as it is today. We cannot see or know what happened in that star's past history that may have led to its present condition. We can only view a present-day snapshot of what exists and have to infer the rest. You'll often see attempts made to measure the age of an individual star, but that always comes along with an assumption that the star didn't have an interaction, merger, or another violent event in its past. Because of that possibility, and the fact that we only see the survivors when we look at the universe today, those ages always come along with massive uncertainties, one in the order of 1 billion years or even more. However, the uncertainties are much smaller when we look at large collections of stars. The collections of stars that form within a galaxy like the Milky Way, open star clusters, typically contain a few thousand stars and only last a few 100 million years. The gravitational interactions between these stars eventually cause them to fly apart. While a small percentage last 1 billion years or even a few billion years, we have no known open star clusters that are even as old as our own solar system. Globular clusters, however, are larger, more massive, and more isolated, found throughout the halo of the Milky Way and most galaxies. When we observe them, we can measure the colors and brightnesses of many of the stars inside, enabling us, so long as we understand how stars work and evolve, to determine the ages of these star clusters. Although there are uncertainties here as well, there is a large population of globular clusters, even within the Milky Way alone, with ages of 12 billion years or more. How certain are we of these figures? Well, it's tough to say. While it's almost guaranteed that the oldest of these star clusters might be between 12.5 and 13 billion years old, there remain large uncertainties about the amount of time required for a star right around the mass of our Sun to begin its transition into a subgiant, followed by its transformation into a full-blown red giant star. It could be 10 billion years, it could be 12 billion years, it could be some value in between. For years, many astronomers who worked on globular clusters argued that the oldest ones were 14, maybe 16 billion years old, but a shift in our understanding of stellar evolution now disfavors that interpretation of the data. Today, we can reliably conclude there is a lower limit to the age of the universe of around 12.5 to 13 billion years from the stars we measure, but that doesn't pin down the age precisely. It's a good constraint to have, but to arrive at an actual figure, we'd like a better method. Fortunately, the universe gives us one. You see, Einstein's general relativity, for a universe filled with roughly even amounts of matter and energy everywhere and in all directions, like ours, gives a straightforward relationship between two quantities. One, the amounts and types of matter and energy present within the universe, and two, how fast the universe is expanding today. This relationship was first derived all the way back in 1922 by Alexander Friedmann, and the equations that enable us to derive how old the universe must be are known as the Friedmann equations. It took us many years to measure the constituents of the universe, but a consensus picture has emerged. Observations ranging from the abundances of the light elements to the clustering of galaxies to how galaxy clusters collide to distant supernovae to the fluctuations in the cosmic microwave background all point toward the same universe. In particular, it's made up of 68% dark energy, 27% dark matter, 4.9% normal matter, protons, neutrons, and electrons, 0.01% photons, particles of light or radiation, and less than 0.4% of everything else, including spatial curvature, cosmic strings, domain walls, and other fanciful exotic components. This picture agrees with the full suite of observations that we have. You have to really cherry-pick your evidence very hard, overemphasizing measurements with large ambiguities while simultaneously ignoring large suites of data to wind up with sets of values that vary significantly from this. So then you might think that everything hinges on the expansion rate. If you can accurately measure that, you can simply do the math and precisely arrive at the age of the universe. Beginning in the early 2000s, and ever since, the best data we have comes from the cosmic microwave background, or CMB, first from the WMAP and then from Planck, and as of July 14, 2020, from the Atacama Cosmology Telescope as well. Those values have all converged on the same expansion rate, 68 kilometers per second per megaparsec, with an uncertainty of just 1 to 2%. When you calculate what that means for the age of the universe, you get a very robust 13.8 billion years, completely consistent with everything we know about stars. Hang on a second, though. You might have heard, and rightly so, that there is a controversy over this. While teams using the CMB might all obtain one value for the expansion rate, the teams measuring the large-scale structure of the universe might agree. Other methods yield a wildly different value, though. While teams using the CMB might all obtain one value for the expansion rate, and teams measuring the large-scale structure of the universe might agree, other methods yield a wildly different value. The other methods, rather than beginning with an early imprinted signal and measuring how it appears today, begin close by and work outward. They measure distances and the apparent recession speeds of various objects, a method generally known as the cosmic distance ladder. When you look at the distance ladder measurements, they all appear to give systematically higher values, between 72 and 76 kilometers per second per megaparsec, about 9% higher on average than the value you get from the cosmic microwave background. You might think then that someone's right and someone's wrong. If the distance ladder team is correct and the cosmic microwave background team is wrong, then perhaps the universe is 9% younger than we think, just 12.8 billion years old. But that's not how it works in practice. The data from the CMB isn't something that can just be ignored, it's something that must be reckoned with. The peaks, valleys, and wiggles that we can see in its temperature fluctuations are a reflection of all these different parameters combined. Sure, the best fit values are for a universe expanding at 68 kilometers per second per megaparsec, and with 68% dark energy, 27% dark matter, and 5% normal matter, but those can be varied, so long as they all vary together. Although it doesn't fit the data quite as well, you can up the expansion rate to, say, 74 kilometers per second per megaparsec, and still arrive at a very good fit, so long as you're willing to change the relative fractions of dark matter and dark energy. With a little less dark matter, say 20%, and a little more dark energy, 75%, a substantially higher expansion rate can still fit the data well, although not quite as well as the consensus values. However, what's fascinating about this is that the derived age barely changes at all if you explore the full range of what is and isn't allowed. That 13.8 billion-year-old figure only comes along with an uncertainty of about 1%, between 13.67 and 13.95 billion years. But it's true that there are still many mysteries left to be uncovered about the universe. We don't know how fast the universe is expanding, and we don't know why different methods of measuring the expansion rate gives us such wildly different results. We don't know what dark matter or dark energy are, or whether general relativity, from which all this is derived, is still valid on the largest of cosmic scales. We don't even know exactly how much of the universe is locked up in which form of energy, it could have more dark matter and less dark energy than we think, or vice versa. The uncertainties are substantial. Similarly, we know that the universe is approximately 13.8 billion years old, but its exact age is not yet clear. Even today, the matter remains open to discussion, as new research could at any moment upend our previous cosmic conception for the age of the billions of galaxies that comprise our universe. That's what happened recently when a new study was released challenging the long-held notion that our universe is nearly 13.8 billion years old. If the findings of this latest research prove accurate, the Big Bang may have taken place 26.7 billion years ago, making the actual age of the universe nearly twice as old as we thought. According to Rajendra Gupta, a theoretical physicist at the University of Ottawa, who authored the study with a new model, we can explain the conundrum that has long puzzled scientists about these ancient galaxies. Gupta said, "Our newly devised model stretches the galaxy formation time by several billion years," Gupta wrote. This age estimate is derived from the universe's expansion rate by measuring the redshift of spectral lines in the light emitted by distant galaxies. The redshift of light is what has long helped to inform physicists' estimates of the universe's age. In simple terms, the thought has been that the redshift indicated the distance of stars and galaxies, and hence the faster they are moving away from Earth. By estimating the rate at which the stars are moving away, scientists can calculate how fast space is expanding into an infinitely growing universe. But the so-called tired light theory that originated in 1929 with Swiss astronomer Fritz Zwicky offered an alternative explanation. Perhaps the redshift we see isn't due to galaxies moving away from us. Instead, Zwicky's hypothesis was that it might be because light loses its energy and shine after traveling a long distance. Gupta proposes that if we allow Zwicky's theory to coexist with the idea of an expanding universe, we can reinterpret the redshift as a hybrid of both of these phenomena and thus arrive at an even more accurate age estimate of the universe. And Gupta goes even further in the study, introducing the fundamental physics idea from English theoretical physicist Paul Dirac that coupling constants govern the interactions between particles. What does this mean? Well, if these constants evolve, then the time it takes for the early galaxies observed in the Webb telescope to form extends from a few 100 million years to several billion years. Better put, it would offer an explanation for the advanced level of development and mass observed in the previously puzzling early galaxies. Knowing when the Big Bang happened tells us the current age of the universe. But how old will the universe get? Will it have an end? Cosmologists are not sure what will happen. It all depends on the nature of dark energy, the mysterious force that is causing the accelerated expansion of the universe. If that expansion continues unabated, it could bring about the end of the universe sooner than you might expect, in a big rip, if you were, where the fabric of space itself is torn apart about 22 billion years from now. However, if dark energy weakens and the acceleration slows or even stops, the universe could have a more prolonged life. If the universe continues to expand steadily, or arrive at an equilibrium with the contractive force of gravity, the universe could possibly survive forever. After 2 trillion years, all of the galaxies beyond our gravitationally bound local subcluster will have vanished over the cosmic horizon, where the universe is expanding so fast that not even light could reach it. By about 100 trillion years into the future, all star formation will have ended. In about 10 to the power of 43 years, that's a 1 followed by 43 zeros, protons inside atomic nuclei would begin to decay, signaling the end of matter as we know it. Finally, after about 10 to the power of 100 years, known as Google, even supermassive black holes would evaporate. All that would be left would be photons, neutrinos, electrons, and possibly dark matter. If dark energy were to somehow switch off, which is possible if it is a variable energy field called a scalar field, then gravity could regain its grip on the runaway universe and cause it to contract back down into a big crunch. However, when this could happen, well, is simply unknown. Well, that's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode. Subscribe if you haven't already, and hit that bell so you never miss out on future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we'll see you next time.